So in section 15.4, we have to compare linear and exponential functions simultaneously and sometimes determine what the situation is, if it's either a linear type of situation or if it's an exponential situation. So to refresh your memory, right, the equation for a line is y equals mx plus b, and m is the slope and b is the y-intercept. And in an exponential function, it's f of x is equal to a times b to the x, or y is equal to a times b to the x. This is the one you'd have to actually enter when we start graphing these things into Desmos. And a is the y-intercept, and b is the common ratio. So, right, the graph of a line, it looks, believe it or not, linear, like a line. But the graph of an exponential function, maybe it's like some kind of curve. So the other thing is some differences, and hopefully refreshing your memory. When m, or the slope, was positive, you know, basically y is increasing from left to right. Right? And then if the slope was negative, the slope, or m, was negative, y was decreasing. From left to right. In exponential functions, if b was a number greater than 1, then the value of y would increase from left to right. I'm just going to write L to R. And if the value of b was a fraction between 0 and 1, right, y is decreasing from left to right. So there's a couple little factoids between linear versus exponential. And let's get into some additional examples so you can kind of compare some stuff, and we can try to model linear and exponential situations. This lower portion of the notes, right? We have a problem that says enrollment. State whether each situation is best represented by an exponential or linear function. So enrollment at a school is initially 454 students and grows by 3% a year. So it's definitely, right, this would be this situation, 454 students times 1 plus 0.03 raised to the power of t. Well, that certainly looks like an exponential equation. And, right, a is 454, the rate is 3%. And t is something we don't know. I don't know how many years they're asking about. But clearly, like, this is definitely also increasing. What about this next scenario? We have a house sold for $546,768, decreasing by 3% a year. This is also exponential. I mean, kind of a dead giveaway, if it's exponential, at least in these scenarios, is the percentage part. So this is going to be, and I think we've actually done this problem in the homework before. Decreasing by 1 minus 0.03, all raised to the power of t. So that's it for this section. Let's flip to the next page. So let's take a look at these situations. We've got June, and she earns a bonus for each sale she makes. So she makes $100 for the first sale, plus $50 for each additional sale. Well, I don't know about you, but that to me looks like a linear equation. Right? There's a slope here, but not necessarily a common ratio. How about this next one? The population of a town increases by 5%. 5% would be exponential. Definitely exponential. The percent should give it away. And let's see, let's assume the population of this town is 20,000 people. And if it's increasing at a rate of 5%, right, that's going to be 20,000 times 1.05 to the t power. Right, when we graph it, you're going to have to, instead of f of t, you're going to have to write y equals. And that t will have to be an x for the Desmos program. Now this one, Mark gets paid an hourly rate, $9 an hour. He must work in Arizona because minimum wage in California is 10. $9 an hour for every hour he works. Let's see. Nope, it's not 9x. If you just wrote that down, I'm sorry. $9 an hour. Plus, he gets 10 cents pay increase for every month he's there. This definitely is a linear equation. A bank account starts off with $500, grows at a rate of 3% a year. This is definitely exponential. And then Sue has a savings account, $5,000. And makes withdrawals of $100 every single week. This is definitely linear, right? There's no exponents involved. $100 for every week. And, 10 weeks, you're definitely broke. You're getting broker. And this last example, savings account, $1,000. Deposits $150 in the account for every single month. Right? It's growing by $150 a month, but it's not growing by a percentage or a ratio. And it's not a multiple, if you will. So this is also definitely linear. So this takes us to the heart of basically what our homework is going to be having us do. At the end of this, when we go to the homework packet, we're all going to grab Chromebooks. They're all going to be opening automatically to Desmos. Nothing else but this website, Desmos, will work. So don't cry to me that I can't check my grade, or I can't look on Google, or I can't go on YouTube, or I can't listen to my music. Hey, that's not the activity. So we're going to do Desmos with our homework next, and that's the only thing that's going to work. So we got a situation now where we have to essentially combine linear and exponential functions and find out where they intersect. And so you got employees A and B, and they each both start off earning $18 an hour. And one of them receives a raise of $1.50 per hour for every year, while the other one, employee B, receives a 4% raise for every year. So we have to model essentially several things. First, what is the initial value for both of these equations, right? What do they both start at? They both start at $18 an hour. And then in the linear example, right, we're going to write the equation for the linear example. Employee A receives $1.50 per year. So they start off at $18, right? That's our B, our initial value. If you have Y equals MX plus B. And then they're going to make $1.50 extra for every single year. So modeled as a linear equation, that's this. Y is equal to 18 plus $1.50x. Definitely a line. All right, here's B. Here's your slope of M. Now let's take a look at the exponential version. The exponential, and this, by the way, is this is for employee A. And then the exponential equation, again, what's our initial value? $18. This is the y-intercept for the exponential equation as well. And then how much is it growing by a rate? A rate of 4%. So that's 1.04 raised to the power of x. So that in Desmos is going to look like this. And then what we're going to do is, in a moment on our homework, I'm just setting up the situation that you're going to have to do in the homework. You're going to go to Desmos, and you're going to type in both of these equations. And what you're going to get is one's going to be a line, and one's going to be a curve. Now they both start at the same spot, right? They both start at $18. But somewhere on the graph, they intersect. And then we're going to have to, on our homework, write the point of intersection and then answer the question. They want to know, when will employee B make more money than employee A? Well, the exponential function is employee B. So the one that's this curve, right, this is going to be employee B. And the one that's the line is employee A. So at some point, basically after this point, employee B makes more money. So, I'll when we get started on our homework packet, we'll get the Chromebooks out, and I'll walk you through a couple as well. So then, like this next example, if we have a stock that starts out at $900 and gains $50 a month, and another stock starts out at $900 and gains 2% each month, when will stock B be worth more money? So we have to first ask, what is our initial value? What are we starting with? Right? They're both worth what in the beginning? $900. And then we have the linear equation is going to start off as y is equal to something. It's going to be equal to how much? $50 a month. $50 a month times x months plus what we started with, right? mx plus b. Just like a line. Y is equal to 50x plus 900. The exponential equation going to also start off y equals, and its initial value is also 900. 900, and then it's growing by a rate of 2%. So 1 plus 2% is 0.02 as a decimal, raised to the x power. And again, we're going to get a graph. When on our homework, we get out the Desmos program. And you're going to have, right, this is stock A, and this is stock B. And one of them is going to be a line, the other is going to be a curve. They're both starting at the same spot. Somewhere they intersect, and eventually, at some point in time, right, whatever this x value is, likewise on the previous example, at some point in time, because in this situation, time is the x-axis, value is the y, B, stock B will be greater than, when is B greater than A? The question. So, without further ado, let's get out our homework packet and we'll begin walking through several examples.